Okay, so in our previous PowerPoint, we talked kind of big picture about the idea of hypothesis testing. We talked about how hypothesis testing is really more or less trying to pick between two conflicting hypotheses, a null hypothesis and an alternative hypothesis. We talked about the different mistakes or errors that you could make in the hypothesis testing process. You could make a type 1 error or a type 2 error. We said that our goal as researchers, as statisticians, is to use a process or procedure that minimizes alpha and beta, right? The probability of a type 1 error and the probability of a type 2 error, that makes those as small as possible. What we generally do in practice is we fix our alpha to be a specified value, often 0.05. And then depending on our sample size, we can get a wide variety of values of what our beta might be, right? Ideally, we want that beta to be as small as possible, but for that to happen, we might have to take a large sample, and a large sample, right, may or may not be something that we can afford. So, with that in mind, let's go ahead and let's look at, right, how we might actually do a hypothesis testing problem all the way from start to finish. Now, what we're going to do here in this PowerPoint is fairly abstract, and the first time you go through it, it might be a little bit hard to digest. The next PowerPoint is going to be a lot, well, 3 very concrete examples that we work through step by step by step. So, if you could find the time, what I might suggest is go through this, try to understand and comprehend as much of what I'm talking about as possible. Then, play the next PowerPoint. Go through the actual worked, written examples one at a time. That will make things start clicking. And then, to really make it stick to the sort of largest extent that it can, go back and then rewatch these. And as you're watching them, having already worked through some problems, right, probably the parts of this that didn't make sense the first time through probably will make sense the second time. So, let's start with kind of an overview. Let's start with actually the Big Mac example we used in our last PowerPoint, where, right, we were FDA agents. We were interested in testing whether mu, the average fat content of a Big Mac, was more than 30 grams of fat. So those were the hypotheses that we set up. Now, to actually perform this test, what would we have to do? We would actually have to go out and take a random sample of Big Macs. We would have to take them to our secret underground FDA laboratory. We would have to liquefy those Big Macs, right, one after another, measuring their fat content as we do so. We would have to compute a sample mean. Now, let's look at 2 possible scenarios or 2 possible situations. If our sample mean, this is situation 1, if our sample mean ended up being 30 grams of fat, what would we ultimately conclude? Well, to be honest, right, there's no other outcome that could more strongly support the null hypothesis, agreed? In fact, to be honest, this supports it so perfectly, so strongly, this so strongly supports McDonald's viewpoint or McDonald's claim of 30 grams of fat on average, that I might almost suspect foul play, right? Maybe some sort of Watergate-esque type scandal that may or may not, say, involve the nefarious Hamburglar. But, right, if we could rule out foul play, this strongly supports the null hypothesis. Hence, our conclusion, right, should be that we failed to reject the null hypothesis. Situation 2. What if the sample mean fat content ended up being not 30 grams of fat, but 9,000 grams of fat? Oh my! What will we conclude then? Well, in this situation, right, this 9,000 is so far above and beyond the 30 grams of fat that McDonald's has claimed, 300 times it, I guess, that we would probably very decisively reject the null hypothesis. We might even declare a national emergency, right, and send in the National Guard to try to shut down all the McDonald's. 2, right, very different situations. Now, what's the big picture of what I'm talking about? The big picture is, right, it's true. There's a lot of technical detail. There's a lot of subtle interpretations. But as we work our way through them, I do not want you to lose sight of the big picture. At the end of the day, hypothesis testing is nothing more. It is nothing more than really generating a sample mean and looking at, right, how far that is from our hypothesized mean. Which is really what? It's really just saying how consistent is my sample and the mean that came from that sample with my hypothesis. If the sample mean is far enough, if it's far enough from the hypothesized mean, then we're going to reject the null hypothesis. And if it's not far enough, that is, if it's rather close to the hypothesized mean, then we're going to fail to reject the null hypothesis. Right? At the end of the day, it's a fairly simple thing that we're doing. The only wrinkle that we have, and I admit it's a hell of a wrinkle, is that we need to formally, defensively, statistically define what is meant by far enough. And that is where all these processes and statistics and formulas are going to come into play. Now, we can do a hypothesis test with the following four-step process. The four-step process will work for us for every type of hypothesis test that we need to do. And here it is. Step 1. Set up your hypotheses. We've already done some practice with that. We did 3 examples of it last PowerPoint. Step 2. You need to construct something called your test statistic. Step 3. You need to compute something called a p-value. Step 4. Using your p-value, you need to ultimately make a decision between which of the 2 hypotheses you support. So step 1, construct your hypotheses, right? Remember, the null hypothesis is always a statement of equality. It's always that the mean is equal to some number. That number is our hypothesized mean. And just like we talked about before, there's 3 cases for what the alternative hypothesis might be. Step 2. We need to construct a test statistic. Now, this step is done the same way regardless of which of those 3 alternative hypotheses we used. Step 2 is always the same. We take our sample, we make the sample mean, and we make this test statistic. We call it Z sub test because the test statistic, right, it's a statistic like we talked about at the end of chapter 4, which means that it has a probability distribution, a mean, a standard deviation. In this case, its probability distribution is a normal probability distribution with a mean of 0 and a standard deviation of 1, which, as we talked about in chapter 4, is what a Z always means. The test statistic is what? It's essentially using the walrus formula from the end of chapter 2. It's x bar minus mu naught divided by sigma over the square root of n. What is that computing? Right? Remember, subtraction is a distance operator. So it's looking at the distance between the sample mean and the hypothesized mean, right? It's literally observing how far is the sample mean from the hypothesized mean. But by dividing it by that sigma over square root of n, it's saying how far is it in units of standard deviations. Now remember, Z is, again, it's always, right, the standard score. It's always the number of standard deviations something is above or below a mean. In this case, it's how many standard deviations our sample mean is above or below our hypothesized mean. Right? So this is basically, it's looking at the distance between the sample mean and the hypothesized mean, right? Which is what we said in our big picture is the important thing. Right? How far is the sample mean from the hypothesized mean? If it's too far, then that means we're going to reject the null hypothesis. But it's converting that distance into a meaningful measurement, right? We said to researchers and statisticians, the meaningful numbers, the meaningful measurements is not the raw values, right? Not grams of fat, but units of standard deviations. And so that's what we're doing with step 2. Step 3. is we basically determine whether our test statistic is large, small, or different enough. Actually, I apologize. That should actually say we determine if the sample mean is large, small, or different enough from the hypothesized mean by calculating something called a p-value. The p-value of a test statistic is the probability of observing a sample mean as extreme as the one we've just observed, or more extreme, given that the null hypothesis is true. So it's basically what? It's basically a measurement of how consistent our sample is with our hypothesis. It's saying, is this sample, or the sample mean generated from the sample, is it consistent with your null hypothesis, right? If this p-value is very small, what does that mean? If the p-value is very small, it's basically saying that the probability of observing the sample mean that you've just seen, the probability of observing the sample that you've had, if the null hypothesis is true, is quite small, right? If the p-value is small, it's saying that the sample you just observed is very unlikely given the null hypothesis. Nonetheless, it's the sample you've observed. It's sitting right in front of you, which then makes you what? It then makes you doubt the truth of the null hypothesis. Now, how we define that idea of extreme that I had on the other slide and I put in quotation marks, and hence how we compute p-values, this step does depend on which of the three alternative hypotheses we are using, right? How we specify our alternative hypothesis will guide us in terms of how we calculate our p-values. So, case 1, I wrote up what that is just to remind you. That's that the mean is less than mu naught. In this case, right, if it's a well-specified hypothesis, and we have every reason to believe that the true mean is less than our hypothesized mean, then our sample mean should be less than our hypothesized mean. And so our test statistic, right, which is the number of standard deviations above or below the hypothesized mean, our sample mean is, our test statistic should be negative. Does that make sense? I want you to think about that and look at the formulas. In this case, if I expect my sample mean to be less than the hypothesized mean, anytime that happens, I'm going to have a negative test statistic. In this case, the p-value is the probability that a normal distribution with a mean of 0 and a standard deviation of 1, right? That's what the z is. The probability that a z is less than our test statistic. To help you remember, notice, the alternative hypothesis in this case is less than, and the way I calculate my p-value formula is less than, right? The less thans match up. In this case, the p-value is the probability of seeing a sample mean as small as x bar, as small as the one observed, or smaller, provided that the null hypothesis is actually true, given that the null hypothesis is true. Graphically, this is what it is, right? Here's our z distribution. It's a normal shaped distribution, centered at 0. In this situation, I expect my test statistic, I expect my sample mean to be below the hypothesized mean, which is equivalent to saying that I expect the test statistic to be negative. So it's going to be somewhere over to the left of 0. The p-value is all that area to the left of the test statistic. Again, showing, as I talked about in the very first Chapter 6 PowerPoint, why this is called a one-sided or one-tailed test. The p-value is essentially just one direction, one side, one tail of this normal graph. Case 2, The alternative hypothesis is that mu, the mean, is greater than mu naught. In this case, right, we expect the sample mean to be more than the hypothesized mean, which is saying that we expect our test statistic to be positive. Our p-value is the probability that z is greater than z-test. Again, notice, the greater than signs match up. My alternative hypothesis is that mu is greater, and my p-value is the probability that z is greater. They match up. This is essentially the probability of seeing a sample mean as large as the observed sample mean or larger, provided the null hypothesis is true. Graphically, I expect my test statistic, as I said before, to be positive, and the p-value is the probability of being that test statistic or further, so it's coloring in everything to the right. This is, again, a one-sided or one-tailed test. Now, the slightly trickier case is case 3. This is the case where we're testing that mu, the sample mean, is not equal to mu naught. It's something different than mu naught. It's something different than the hypothesized mean. In this case, the p-value, here's our formula, the p-value is 2 times the probability that z is greater than the absolute value of the test statistic. This is the probability of seeing a sample mean as far from mu naught or farther, given that mu naught is true. So remember, case 1 is the probability of the sample mean being small or smaller. Case 2 is the probability of the sample mean being as large or larger. Case 3 is the probability of the sample mean being as far from the hypothesized mean or further, right? Case 3 is saying could be higher, could be lower, right? Combining both of those ideas or concepts is sort of how far it is from it, right? Or further. Let's try to talk about the intuition behind this formula on the next slide. So here's our picture. Now, part of the problem with case 3 is that since we think the true mean is something other than mu naught, we don't have any a priori, we don't have any ahead of time expectations as to whether the sample mean is going to be more or less than the hypothesized mean, which means that we don't know whether the test statistic is going to be positive or negative. We have no expectations for that. However, we do know what? We do know that the absolute value of the test statistic will be positive. Agreed? Remember, absolute value is really the distance of a number from 0 on a number line. That distance is always measured, right, in positive units. So like the absolute value of positive 7 is positive 7. The absolute value of negative 3 is positive 3. The absolute value sort of strips away any negative signs. So, although I don't know whether the test statistic is positive or negative, I know its absolute value will be positive. So I focus on that right-hand tail. I look at the probability that z is greater than z-test. That's the area of that right-hand tail. Now, the case 3 is the two-sided or two-tailed test. I want to know actually the probability of being that many standard deviations away from the mean or further. So I also need the leftmost tail. However, by the symmetry of the normal distribution, these tails have the exact same area. So if I find the area of the right-hand tail and I double that, right, which is essentially multiplying it by 2, I can get the total area of both tails, which is what the p-value is. Right? So a little bit of intuition behind that formula. Step 4. This is where our alpha comes into play. If we want to construct our test, if we want our test to have exactly some alpha percent, right? Often this is 0.05. So for example, if we wanted to have exactly a 5% chance of a type 1 error, no more or no less, how do we create a test that satisfies that? Well, we do it by using this criteria for making our decision. If the p-value from step 3 is smaller than our pre-selected alpha, then we're going to reject the null hypothesis. So remember, I said when I defined the p-value, the smaller the p-value is, the stronger the evidence that we should reject the null hypothesis. How small does it have to be? Well, in this case, we're basically saying it needs to be smaller than our pre-selected alpha. If it's not, well, then it's not small enough. Anytime the p-value is larger than or equal to alpha, then there's not enough evidence to reject it, so, right, the only other possibility is we fail to reject the null hypothesis. Now, I know this is a lot to absorb in a very abstract level without really seeing any examples. So, before you panic, I want you to maybe take a break, take a breather, go treat yourself to a walk, right? Maybe, I don't know, go indulge in a snack or a dessert of some kind, perhaps something healthy like fruit or vegetables, and then reload the next PowerPoint. It'll go through some examples, and hopefully that will help it make a little bit of more sense.